Okay, next up we have an OpenCL presentation from Tomasz Bednarz.
So I'll be talking today not only about OpenCL but as well, different technologies that we use inside CSIRO, such as OpenGL, OpenCL, and other technologies, that we use for our scientific projects. So, to introduce myself, I work at CSIRO, which is basically based in Australia. So we are based in Australia down under, so it's a very beautiful one. So if you have opportunity to visit Australia, just please come along, and as well please visit CSIRO as well. So to give you just general introduction to our organization, CSIRO is Australia's national science agency. It's one and the largest and more diverse in the world. So we do a lot of scientific breakthroughs in science. We are ranked in top 1% in 14 research fields, and main objective of our organization is to support Australian people and as well Australia. So we have a bunch of different national research flagships, as you can see in here. So we do a lot of stuff on climate adaptation, energy transform, food features, future manufacturing, light metals, and so on and so on. So basically, from my perspective, trying to utilize newest technologies that are available in the market to do better science and speed up Australian science as well. So in these days, there is big need for computational and simulation sciences. Okay, so there are several problems we have still to solve. So the technology we have today is still not good enough for some of the scientific problems we have to solve. So one of this is ASCAP, which is Australian Square Kilometre Array Pathfinder. It's basically, to tell you a bit more about it, it will generate more information that is contained on the entire web in just 1 week. So you can imagine how much data we will be gathering. So it's basically a set of different antennas are getting information from this space, a set of antennas connected together to get very high resolution information from the sky. Another problems to be solved is climate change problems that we are working on, and as well genomics revolution, which is bringing more and more data sets to be processed. So this slide as well shows some of emerging science challenges. So some of them is we use advanced sensor networks to monitor the water resources in Australia. As well, we use visualization capabilities. I will show on the next slide how to visualize different data sets using OpenGL, for instance, and combine as well with OpenCL. We have as well people working on computational fluid dynamics and speeding up computational fluid dynamics, and as well predictive mineral discovery. So I'll tell a few words about that later on as well. So inside CSIRO, we build capability and computational and simulation sciences. So there are 4 main branches. So one is imaging, processing, and visualization. So it's basically computational imaging. So we use OpenCL to speed up imaging, for instance, and to do image processing and image analysis. As well, biochemical cycles, computational material design, so I'll show some results as well, and data constraint from material modeling, so like Australian synchrotron, for instance, which is one of our, will be one of my good examples to show you how to use visualization these days for large data sets. And today, we need standards, okay? So basically, Khronos Group is an excellent example of consortium which is creating standards, and we need basically unified standards. So as you can see, the situation is maybe everybody wants to create their own standards, but the best way to go, I think, will be stick to standards, that you already have available on the market. So coming basically, in terms of OpenCL, OpenGL, so this slide shows integration of different technologies that you use currently supported by Khronos Group. So I don't need to say anything more because it was covered before. So just wanted to show this slides basically to show the connections in between the different technologies such as OpenCL, OpenGL, OpenGL, and so on and so on. And we need supercomputers, so we support such supercomputing and high-performance computing inside CSIRO, again, to speed up science. So I show two sides. So how it was in the past. So in the past, we had like a SIGGRAPH, which was Serial Automatic Computer. It was built in 48. It was fourth computer in the world. It was doing one operation per second. You can imagine it was very, very slow. But it was still, allowing to do some scientific breakthroughs, and it was used heavily for doing simulations on weather forecasting and banking systems, for instance. And the newest one is our Serial GPU cluster. So it's currently, using it to speed up our numerical simulations, for instance. So it features 1024 Xeon CPU cores, 32 gigabytes RAM per node, we have like 64 NVIDIA Tesla S2050 GPUs. We have like a network storage as well. And as you can see, it gives us, 52.55 teraflops double precision using CleanPack. And currently we are ranked 212 in the latest top 500 list and 13th in the Green 500 list. Well, if you are a supercomputer, you know what that means. So basically, why we support GPUs these days and why we are trying as well to support heterogeneous systems. Basically, today's GPUs give us, excellent ratio of money to computation ratio. So we have basically lower cost per flop these days. We have lower power consumption and as well higher computational density. So as well we have a smaller real estate. It's like the computer I showed was doing one operation per second. It was taking all space of 2 garages, I think. So it's like a huge. So this day you have everything to small cards or small chip. It allows us as well to do supercomputing on the desktop, and as well supercomputing is coming to your pocket. So when you use technologies such as OpenCL, you can, for instance, execute your simulations just on your mobile in the near future. So few core is the past, so we go towards like multi-core architectures. So basically trying to utilize those as well. So to support science, like OpenCL for instance, we basically have GPU cluster supporting our science. It allows us to reduce time to discovery, and as well allows us to increase productivity and increase depth of our simulations and data analysis. So we always ask these questions: what would you do if you have, like possibility to do things, for instance, like 1,000 times faster? So that is basically, allowing us to really speed up and really, like discover things in a better way and do things in a better way. So basically, by doing that, we increase quality of scientific results. So now I switch a bit to talk about some visualization capabilities and collaboration platforms we have in our organization. So we're basically coming from this e-research program. As a scientific organization, we do standard research planning, we do collaboration of these different groups inside the organization, data collection, data management, computation, discovery, and eventually we have some publications. And the advanced collaboration platforms we support basically like we have like several collaboration platforms sitting in the organization. So when we need to speak with people from different cities, different locations, we can use those platforms to share the screen, to share instrumentation, for instance, microscopes, and so on. And the technology we use for that is OpenGL, of course. And as well, we have as well SIDO, we call it CAR system, ultra high resolution visualization systems. So it is a bunch of different monitors of high resolution connected together in matrix. So in this way, you are able to display high resolution imaging coming from different scientific outputs on the screen. So for instance, like geophysical outputs or very high resolution, reconstruction from CT scans. Advanced visualization capabilities inside CSIROS are as follows. We have like remote visualization, we do stereoscopic display systems, we have advanced visualization software packages, so we use several different packages there so that are available to our scientists. We have as well access to partner visualization facilities, so we collaborate with many different organizations inside Australia and outside of Australia. And we do as well visualization support and consulting. So remote visualization architecture is shown in here. So we use several different technologies, support OpenGL of course, and we have like virtual GL to do things remotely, for instance. So you can see like a standard connections of the servers and like the viewers, for instance, and people that can share similar sessions using those techniques. We go as well to support immersive environments. So we have for instance like a panoramic display systems. So this is like a kind of hemispherical dome. You sit in the middle of the hemispherical dome, and you are completely immersed with the environment being displayed there. So in this way you can do, for instance, like beautiful telecollaboration scenarios, so allow people to control remotely some big machinery and so on, or display your scientific results in very self-telling way. So this animation shows the scale of the 4-meter hemispherical dome we have in the organization. So that's the person, and you can see it's actually huge, and you can feel when there's movement inside the dome. You can really feel like being immersed with the whole environment. So this dome is actually built in Virtual Mining Center, which is located at KITE in Brisbane. So it's basically, they use it for visualizing, geological data sets and as well the mining industry. So I'll show you some results as well in the next slides. You'll see how you can do it. To send my message as well, was very important. So I'm just trying to go from a more scientific point of view. I saw a lot of amazing presentations, on computer graphics, for instance, at these conferences. The problem is, that people sometimes are not verifying, like the results with science or with physics, So I think it's very important. So I show you like one of the examples, like the work that I was doing before. So it's like CFD code development workflow for developing code in OpenCL. So basically developed, like CFD code, starting from scratch. So basically using this kind of slides for teaching people how to do stuff. So we're coming from the equations, like Navier-Stokes equations in terms of, if you look at CFD simulations especially. So then you have to do discretization of them, implement them, and you need to do verification whether the results you get into are with agreement with the real world, right? Then once you have like the proper results, you will be trying to transfer the CPU code to GPU code, and again you need to do verification and you get the results. So in order to do it, you can do, for instance, like a physical experiment. So this shows like a physical experiment that I was carrying out. Like for instance, this one is using liquid crystals to verify temperature distribution, for instance, in water. And by doing that, you can have, for instance, velocity profiles and as well temperature profiles, and you can compare your numerical results with the output of it. So once you verify the numerical algorithms you're using, you can extend it to different cases. So this one shows PIT and PIV method. So it's particle image development, particle image velocimetry method. So some of the image processing used for doing calculations of these methods used OpenCL. So basically you do like an experiment with liquid crystals, and by analyzing patterns, like color patterns, you get temperature profiles and velocity profiles at the same time. So by using that, you can, as I said before, verify your numerical code with the real physics. And this one shows discrete element methods and SPH results done in our group at CSIRO, our division by Khronos Group. So as you can see, there's like several different applications, and they're using it to combine actually like the visualization together with like a physical simulations with different various applications for industry. So for typical fluid solver, we have basically two loops. One is inner loop and one is outer loop, and they are iterating, like our time steps with the time link. So basically, this is showing basic. I won't be going into much detail because I have limited time. So just only tell you, that once you start you need to start usually when you develop, like for instance, OpenCL based code, you need to start with something which is working on CPU based fashion, for instance, like to be sure that everything is working properly, we're getting proper results. So once you do that, and verify that you can extend your stuff into OpenCL, for instance, and OpenGL. So this one shows, like this blue boxes shows, what you do, like in order to inject, OpenCL code inside your, for instance, beforehand written CPU code. And as well, you can use this interoperability between OpenGL and OpenCL, for instance, to do like visualization once you're calculating every next time step. So in the next few slides, I show you as well like some of the projects that we do with multi-sensor assimilation and teleoperation. So role of sensors. So sensors are very important. Basically, they show us how the world is sensed by us and how we can actually use this information to monitor or different machinery, for instance, and how to check the pressure, temperature, forces, distances, and so on. So we use a bunch of different sensors, and one of the stuff that we use is like INS systems that we use for underground mining, geolocations. So if you go on the surface, you need to see satellites in order to geolocate your position of your vehicles on the earth. But if you are underground, you don't have this opportunity. So you basically do integration of acceleration in order to geolocate the machinery. So then, when you have like information from the real sensors, you can integrate those informations together with like OpenGL rendered virtual reality worlds. So this one shows, underground mine, which is rendered in OpenGL, and it uses all the information taken from the sensor networks. So now as well, we use like this fancy camera such as Ladybug camera from Point Grade to do like a teleoperation project. So basically it was used, for instance, for ship loaders or monitoring, different environments, in industry. So this camera has basically 6 cameras, 5 around and 1 on the top. And we're trying to do like real-time video streaming and real-time, put virtual camera inside the sphere and rotate inside the field of views. So as you can see, we got like 6 different images grabbed like it was like 15 frames per second and mapped on the virtual sphere, and then put the virtual camera inside and we can rotate around. As well, we needed to generate like a fisheye image in order to project it correctly on the dome. So it's OpenGL vertex shaders for that. And as well, some data fusion, so trying to connect point clouds data sets coming from, for instance, from laser scanners together with information from the cameras. You could get like a color information or color here point clouds. Another application is e-learning. So we developed, like distributed collaborative framework in CSI. We also have like a local user, which is sitting somewhere in the front of immersive environment and using different sensors to talk with the virtual reality world that you built in OpenGL or virtual reality engines such as Unity, for instance. So we defined several virtual reality scenarios like Mars virtual reality, real-time mindset, and ebook that I will show on the next slide as well, and displayed it on the big screen so the user that was observing like virtual reality was kind of immersed with the whole environment. So we use for this OpenGL, of course, and very important thing I think here is I'm looking forward to get a bit more hands-on Khronos StreamInput. I stole these slides from the website, but basically to make you aware that you can use basically this technology, which is an amazing way. So at this stage, everybody was developing own way to talk to sensors, but if we have some unified way, it's going to be really, really powerful. So you don't need to think much, just use the technology and integrate it into your solutions. So for e-learning or e-education, so it's usually like proven that if you read a book, you remember only 10% of it what you read. If you go to a lecture, you remember 20% of it, but if you experience something, you will remember 80% of it. So we're trying to utilize like the newest technology in order to have like bigger impact on education. So this shows like a prototype of the project we developed at KITE for enhancing e-learning. So it has basically like the big book rendered on the big screen, and you have a bunch of different pictures, and as well like the gestures on the corners. And basically, when you have, like, for instance, data glove sitting on your hand, you are able to send gestures to the system, and the system was responding. So, for instance, if you send the proper gesture, you go inside the virtual reality world like this, and you can play with, for instance, mining machinery. So you can imagine this kind of technology can be beautifully used for any kind of engineering on physical worlds. So this shows as well, like some additional things. So we have as well use iPhone to talk with the whole system and so on. Another thing that we use inside CSIRO is autonomous vehicles. So we had a vehicle that was that used a bunch of different sensors such as lasers, cameras, stereoscopic cameras, and so on. So we're trying to unify those things as well. So again, computer vision standards that are coming from Khronos are going to be really powerful thing to use in terms of speeding up our processing. So some of the experiments we used as well is like tested, like human system interaction experiments. So it was like testing whether immersive environments are better against non-immersive environments. So that was an experiment we carried out. Well, if you'd be interested, I can tell you a bit more in detail afterwards, because as I said, my time is limited here. So we're basically trying to enhance collaboration in between on-site and off-site users. So they had to solve the task to pass the maze. So everything was done remotely. So we used basically, like a TCP socket to send the video streams and compress video streams. However, OpenGL was used to render the things and stitch the images live. So the images were coming 15 frames per second from my back camera, and as you can see, the mouse. For some reason. Anyway, so you can see the user, which is sitting in the front of the big screen and using joystick to operate the machinery and as well change the field of view. So this kind of things, we need like unified standards to talk with the different sensors. And computer vision, so a bunch of different things in computer vision, stereo vision for instance. So we use like a OpenCL as well, developed own libraries for doing stereo vision as well, accelerated stuff using OpenCL. So the main idea was to do, well, while we were using, for instance, data gloves, it was kind of nice, but you don't want to wear data glove every day, so we wanted to have like gesture recognition using your hands. You could send the commands to the system. So stereo sound vision, so reconstructing the world from stereo vision cameras and as well laser scanners and odometry and so on. And as well photogrammetry, which is basically very powerful techniques for reconstructing 3D geometry from just images. So you can use OpenCL for speeding up the processing of such things. And the newest being workflows and cloud computing. So this is like a cloud computing is this buzzword coming over and over these days. But what we are trying to do, we have like a bunch of different software packages, and we're trying basically to speed up like the main routines using GPUs. So those are for biomedical applications. So if you imagine some image processing, and you have like different images coming from different image modalities. So basically trying to, for instance, do reconstructions of images from CT scans and do filters using OpenCL to speed it up. So we need some kind of, fast, coherent cloud-based image analysis processing tools. So utilize as well the resources we have, like GPUs resources we have inside CSIRO. So in order to build, like this complex functionalities, we're trying as well to make things very easy to our scientists. So we try to create like workflows from the simple blocks that can talk to each other. And the scientists, they don't necessarily need to know how it works, because not everybody is specialized in image analysis process. They want to achieve specific tasks in the easiest way possible. So that's what we are trying to achieve with this stuff. So some of these blocks can be actually executed using OpenCL, and as well many of them are using visualization for visualizing the output of the processing. So maybe skip this one, so it shows basically like integration of different technologies we have, but I show you some results. So we use basically Drishti for rendering of the results. So it's open source volume renderer, so if you haven't heard about it, just browse the website and download it. It's beautiful stuff what you can achieve. So this one shows reconstructions of city image from Australian synchrotron. So Drishti itself uses OpenGL and GLSL, GPU accelerated computing. It's highly interactive, so you can play and create animations. And this is used basically with connections to Australian synchrotron, so with a bunch of different reconstructions in Australian synchrotron. And in order to do it, remotely, we need as well multi-connections with different facilities inside Australia. So that's how we do it. So we have like software sitting in different places, and Australian synchrotron is doing, scanning of the, for instance, like living animals, or like stones or plants, for instance. And we developed as well software which is called XLI, and it uses OpenCL to reconstruct, to speed up reconstruction of the CT scans. So in the software we have basically like a tick box you click that you want to execute something remotely, and you apply, and it does everything automatically for you. It goes to our GPU cluster, execute things very quickly, and gives you results almost in no time. So as you can see in here, we have like different volume reconstructions, so we can go from 161 hours up to 41 minutes now using OpenCL and GPU clusters that we have in Australia. So this shows as well some additional results done using the same software. So city image of the rainbow and as well some pine. And the next one is very nice as well as acacia plant sample. So you can do, like volume visualization. So it's again, everything is rendered using Drishti, and it uses OpenGL for doing that. So you get fully interactive things what you can do, what you can achieve in there. So if you haven't heard about it, just go and try to Google it and get the software. It's for free or open source. And the last two slides is like events. So just wanted us to announce like a VSP, which is basically trying to connect visualization and science with biological data set visualization. So there's gonna be like a conference happening in Europe. So if you're interested into biomedical applications and visualization and connecting art with science and visualization, just feel free to come for this one. And the next one is OSVIS. So Derek, you want to say a few words about OSVIS?
Go ahead.
Okay, so OSVIS is basically the small, like the conference we organize in Australia, and we organize it every year. So this year was just 3 weeks ago in Sydney, and next year gonna be in Perth, so it's gonna be organized by Derek mainly. So if you have any questions, just ask Derek. So what we're trying to do, like 2 years ago or like a year ago, we organized OpenCL workshops. So we invited people from industry, like from NVIDIA and AMD, and they give presentations about OpenCL in particular. And this year we have accelerated computing workshop, which was about integrations of different technologies. So not only OpenCL, but as well CUDA, OpenGL, and as well high performance computing. So next year we're gonna be going back to OpenCL. So I hope Khronos will support us with this event, and you are welcome to come. We'll be trying to do it most probably just before SIGGRAPH Asia next year. So it's very nice. If you'll be flying to SIGGRAPH Asia, you can go through the Perth and enjoy our down underground and sea kangaroos and other creatures.
What date is that?
Oh, we haven't decided yet, but it's gonna be just before SIGGRAPH most probably to make it easy so you can go all around the world. Okay, so that's it from me. Thank you.
So, of the various Khronos APIs, what are we missing? What do you most want to see next in any of the APIs?
We're looking mainly in scientific areas, like this OpenCL, for instance. I'm really strong, trying to support OpenCL inside the organization. Even some of the people are saying, like CUDA is a bit more evolved. But what we need, is like this, for instance, like a big public operation, like, possibility of building libraries, scientific libraries, not sharing, the source code, for instance, because you may release, beautiful libraries from ourselves, but we don't know to expose our IP, in terms of source code, for instance. So.
Yes.
And as well, I'm looking, as I said, like this computer vision areas and as well stream input standards. We're gonna be running in this industry.
Yeah. So as you know, the SPEAR working with OpenCL is trying to solve that source distribution issue.
Yes, yes. No more questions. Thank you.